All right. Welcome back again, ladies and gentlemen, distinguished guests. We will now proceed to the fourth keynote presentation delivered by Dr. Harold Ruiz, Mr. Joseph Akinwumi, and Miss Yaching Shao from University of Leicester, United Kingdom. To lead this important segment, we will now invite our moderator. Please, the stage is yours.
Okay, good afternoon, everyone. Okay, are you with me now? Yes, okay, very good. So, before we continue, I'd like to take a moment to acknowledge a distinguished academic who, although unable to join us live today, has graciously shared his support and interest in our conference. Please allow me to introduce Dr. Harold S. Ruiz, Associate Professor at University of Leicester, United Kingdom, and head of the Great Research Group, which stands for Green and Energy and Transport. Dr. Ruiz is internationally recognized for his work in electrical machines, power systems, and superconductivity, with over 36 published papers and a strong track record of interdisciplinary collaborations. He also led pioneering research on fault current limiters, cryogenic application in energy systems, and solar power optimizations, including studies relevant to Southeast Asia. His group actively connects engineering with physics, mathematics, and material science to address global energy challenges. Although Dr. Ruiz is unable to be with us today due to prior academic commitments, he sends his warm regards to all participants and expresses keen interest in future collaborations, especially those who focus on sustainable energy and smart grid innovations. Okay, let's take this opportunity to appreciate his contributions and look forward to welcoming him in the future editions of these forums. Okay, please give applause for Dr. Ruiz. Okay, now let's move on to our speaker. Good morning, Joseph. Are you with
Good
me
morning.
now?
Yes, I'm with you. Can you hear me?
Can you hear my voice clearly?
Yes, I can hear you clearly. Can you hear me?
Okay, thank you. It's good an honor for me to welcome Mr. Joseph Akinwumi, a PhD candidate in engineering at University of Leicester, United Kingdom, as our keynote speaker. With a strong academic foundations in electrical and electronics engineering, and a research focus on advanced control strategies for power converters and electric drives, Mr. Akinwumi brings a compelling blend of technical depth and forward-thinking innovation. His expertise spans model predictive control, parameter estimation, and machine learning application for motor drive systems, contributing to the electrification of transportations and the development of next-generation industrial technology. Today, he will present his latest work entitled ANN-based online parameter correction for PMSM control using spare decoding algorithm, which explore the integration of artificial neural networks and decoding techniques to enhance precision and adaptability in motor control systems. Please let us warmly welcome Mr. Joseph Akinwumi to the stage. Okay, the time is yours, Joseph.
Thank you. Hello, everyone. Sorry, let me share my screen. Sorry, I'm unable to share my screen currently. Can you hear me? Hello, can you hear me? Can you hear me?
Excuse me?
Can you hear me? Hello.
Do you have any problem to share your slide?
Yes, I have problem sharing my screen. Okay.
Okay.
Can you hear me now?
Yes, we can
Good
see
morning,
your
everyone. Okay. Good morning,
Great.
everyone. My name is Joseph, and I'll be presenting ANN-based online parameter correction for permanent magnet synchronous control using sphere decoding algorithm. So the aim of this work was to implement an artificial neural network for long prediction sphere decoding algorithm for permanent magnet synchronous motors to aid parameter identification during parameter mismatch. So we'll be using two matrices for this study, which is the total harmonic distortion and the Lyapunov stability to prove stability, because currently there is no experimental data here. So Lyapunov stability, we hope, stands as the theoretical foundation. So for a closed loop system to be stable, the Lyapunov function must be positive definite. That means it should be negative or non-positive on average. So before we go into the ANN part, I would like to first discuss the importance of long prediction horizon. So the reason why we use long prediction horizon rather than other control is because long prediction horizons reduces harmonic distortion, it improves robustness to variation in parameter, and it improves closed loop stability. So for us to use that long prediction horizon, there are some techniques called branch and bound method that can be used. And to apply these techniques, we have to reformulate our mathematical problem before we can use the sphere decoding algorithm or other algorithms such as the K-based sphere decoding algorithm. So this involves us redefining our input and output sequence for the long prediction horizon and making them suitable for these advanced optimization techniques. So for the sphere decoding algorithm, we need some system formulation, especially it's being in state space. So for us to do that, we have our state space equation, which is our system matrix, our system parameter matrix, and our output matrix, which is represented here. Our states to consider is our currents, and our output is the switching states of the two-level three-phase inverter. So the sphere decoding algorithm's mathematical formulation is showed here, which is the A matrix, which involves the resistance, the inductance, and the speed. The B matrix is the inductance, and we have our Park and Clark transform. So the way the SDA works is that it finds an unconstrained solution, which is the best solution to power converter, but it cannot be applied. So using the sphere decoding algorithm, what is done is it looks for the closest feasible inputs to the inverter and applies it directly to the power inverter. So the point of adding a artificial neural network to this sphere decoding algorithm and the permanent magnet synchronous motor is to help with parameter mismatch. So when we are making control for the motor, we have to use a mathematical model for the system in the model operative control. But most of the time, our mathematical model is not always accurate with the motor. We could find one very close to it, but during operation, maybe when the permanent magnet is running over a long period of time, conditions such as heat or magnetic saturation can either increase or decrease the parameters in the motor, while the parameters in the controller stays constant. So what happens now is that the performance will degrade. So the point of this artificial neural network is to serve as a link between the controller and the permanent magnet. In so doing, when this mismatch occurs, the artificial neural network can effectively update the parameters in the controller. So this image here is the three-stage workflow of how the ANN parameter works. So first, we implemented the PMSM drive model with the sphere decoding algorithm. We defined the mismatch range for us to simulate, to generate the training data. So the mismatch range is between +50 and -50. So the two parameters we are varying would be the flux and the inductance. The inductance and the flux are chosen because they are both of the values, parameters that have effects on the performance of the PMSM. So after doing that, the flux and the inductance are varied across a positive 50% range and negative 50% range. So in so doing this, the flux and the inductance are the inputs, and the mean and ripple are the output value for data collection. So after we have collected that data, we go on to the next phase, which is the training stage. Now, for the training stage, the ANN is trained offline to estimate the inductance and the flux. So previously, when we were training the data, we use the flux. When we are generating data, we use the flux and the inputs, flux and inductance as the inputs, and the mean and ripple as the outputs. But now, when we are training data, we want the ANN to be able to identify the inductance and the flux online. So we use this approach called an inverse application of AI, meaning when we are training the data, the inputs becomes the outputs, and here the outputs becomes the inputs. So in so doing, online, we could use the mean and the ripple, which we got as the outputs for data collection, to be the inputs during online estimation. And the input, which is the inductance and the flux, will be our output, which will be updated online. So the next image to be showing in the next slide, which shows the training performance. And after doing that, after training it, we can integrate it into the PMSM for mismatch scenarios, which it can help the controller with. So these are ANN architecture. We use the mean and the ripple as the inputs. The mean and the ripple is gotten online and stored through a buffer, and the output will be the inductance and the flux, which will be estimated online. Now, our ANN performance, since we're predicting two values, which is the flux and the inductance, we train this value under the 70-15-15% training split. 70% of the data for tests, 15 for training, and 15 for validation. So this was our performance, which for the flux, the performance was very good. And for the inductance, it was good, but it was not as good as the flux. So this is the operation of the permanent magnet machine, the current in the DQ axis. So for a scenario without parameter mismatch, we have our total harmonic distortion as 12.98% in the phase A current. But when there is a mismatch that occurs, so while for the previous slide here, the parameters in the controller and the parameters in the machine are the same, meaning there was no mismatch. So in the first scenario, we took the first scenario mismatch as a point where the machine parameter becomes higher than the controller parameter. So in that case, the ANN starts to work at the 0.042 time frame, and it gathers the data. After it gathers the data, at the 0.08 second time mark, the ANN activates and updates the parameter in the controller. So in the first half of this diagram, the data collection, the ANN is off. The machine inductance was 3.3 millihenry, and the controller inductance was 2 millihenry. The machine flux was 0.76 Weber, the controller flux was 0.71 Weber, and the THD was 12.54. So when the ANN finished getting data and predicts the values, it predicted the controller inductance as 3.2 milliweber, the machine flux accurately as 0.76. And in this way, we were able to reduce the total harmonic distortion from 12.54 to 12.11. In the next scenario, the machine inductance reduced drastically to 0.7 milliweber. The controller inductance stays the same at 2 millihenry. The machine flux increased, and the controller flux stays constant. In this place, the total distortion was much, which was 30.51. The current in the DQ axis had lots of ripple, which was seen in half of the diagram. But when the ANN came on, it was able to estimate the machine inductance to 0.76 in the controller, was able to predict 0.76 in the controller and update the controller flux also to 0.94, which reduced the THD by a small amount. But as can be seen in the dynamics of the current system, there is lesser ripple across the right end of the ANN compared to the left side. So another scenario was with increasing the machine inductance to 2.9 and the machine flux to 0.66. So in this scenario, on the left side, we have a higher THD of 11%, and on the right side, we have a lesser THD of 10.68. That's because the ANN was able to update the machine inductance in the controller to 2.95 and it's 0.65. So long prediction horizon occurs when we go different prediction steps. Sometimes you can go higher. So the previous diagram showed a 3-step prediction sphere decoding algorithm. But to evaluate the applicability of the ANN, we did it for 2 prediction horizons, which is the 3-step horizon and the 2-step horizon. So currently now we are focusing on the 2-step horizon after finishing the 3-step horizon. So the approach was pretty much the same also. We generated data for the 2-step horizon the same way we generated data for the 3-step horizon. Now for the 2-step SDA with no parameter mismatch, the total harmonic distortion was 10.89. So entering the first scenario with the 2-step SDA mismatch, the machine inductance, the permanent magnet synchronous motor, the motor drive inductance was 1 millihenry. The controller inductance still stayed constant at 2 millihenry. And the machine flux also changed. So at first, we could notice the distortion on the right side to be 14.18%. After gathering data, the mean and the ripple, the ANN was able to update the controller, not accurately. This was 0.89, and the controller flux was 0.6. But then we're also able to achieve a reduction in our total harmonic distortion. And to the left side, you could see a deformation in the wave at the 0.042, but this was eliminated at 0.12 when the current in the DQ axis reaches the area. Another scenario which we took was the machine inductance, where it increased to 1.5 and the machine flux increased to 0.78. The THD was at 14.34%, but after data collection using the mean and the ripple currents, the ANN was able to update the controller inductance to 1.46 and the accurately able to identify the machine flux at 0.78, which it operated in the controller. Now the THD is now 13.78, which is a reduction. Now in this third phase, the machine inductance was taken at 3.3 millihenry, the controller inductance was taken at 2, the machine flux was taken at 0.85. Now at this end, this result was different from the rest because the THD here before the ANN collection is 10.96, but at the other end, the THD was 12.65. So the ANN has some limitations in the fact that the controller inductance estimated was higher than the machine inductance, which is the first case rather than the other case. So in this scenario, the THD increased by 12.65, which is one of the limitations of the ANN. Now, we did a reverse scenario where after the ANN has updated the parameters in the controller, what will happen when the mismatch, because parameter mismatch happens when due to temperature or issues with the coil. So in a scenario where the machine cools down or a fault is fixed in the coil, the values in the controller has already been updated, but what happens if the machine goes back to its original parameter? That means a reverse mismatch will occur, where the controller values are now higher than the machine value. So we did a test for the ANN to be able to revert the machine parameters back to its actual value. So in this scenario, we start with the controller having a higher value of 3 millihenry and the machine inductance being the one with normal value now. At the end of the ANN, was able to update the machine parameters closely back to 1.9 millihenry and 0.71 millihenry. That's for the 3-step. And for the 2-step, we tried it also, where the controller inductance was at 1.5 millihenry and the controller flux was at 0.61. After applying the ANN to this, the controller inductance was updated to 2.1 and the machine flux was updated to 0.71 to revert the controller parameter back to its normal states. Now, we also stated that for earlier, we had two performance metrics, which is the total harmonic distortion and the Lyapunov stability. Now, the Lyapunov stability, as stated earlier, means that the mean value of the average Lyapunov should be negative. So at this point, we have on each, these 9 diagrams represents the previous 9 diagrams that I've presented throughout this presentation. So we could see on each diagram, there's a pink shaded area. So this pink shaded area is taken as pink because you can see sharp spikes in them. This is because of the transients, where in the previous diagram, the current went up, went down. So these side are taken as the initial transients of the motor. So the part that was taken as the mean was the part after the transient. So other spikes you can see there is because the machine current also went up or down. That's because of due to change in the torque. So on each diagram, we could see that the mean value is a negative value, which proves the stability of this ANN with the original sphere decoding algorithm MPC. So finally, we did the runtime, the computational complexities, because ideally one of the disadvantages of the sphere decoding algorithm or the disadvantage of long prediction in general is that it has high computational time. So to include another component, which is the ANN, into the already established high computational time to take more time. So to prove this feasibility of the study, we did a execution time for the ANN to prove that the ANN only adds little burden. So in the diagram above, the sphere decoding algorithm, if the diagram above includes 4 parameters, which is the mean, standard deviation, the minimum value, and the percentile. So for the sphere decoding algorithm, in general, it has a high computational time of 52 microseconds per control cycle. Now, with the ANN itself has a very low control time of below 2, which is actually below 10% of the computational time of the SDA. So this makes it feasible because it's only adding very little computational overhead to the sphere decoding algorithm that already has a high computational time. So the future works in this, the next stages after this work is the hardware and loop verification using a disk space box and a plex box. And also, I stated in one of the images where the ANN updated the value in the controller and the THDC increased. This also led way to motivation for approaches called model-free approach, where we don't use a mathematical system anymore. We don't use the AI anymore. We just use data, the data in the currents for prediction and also experimental validation of this work. So thank you for listening.
Okay, thank you very much for your insightful presentation, Joseph. Now we will open the floor for questions and discussion. Maybe from the on-site presentation participants. Okay.
Hi, Sir Joseph. I, Wilson Septadi Wijaya, will guide the Q&A session. So there's a question on the chat box. So the question is, how the calculation or method meet real condition?
Okay, so the question is actually not generic. So I'll answer it in two ways. How does the calculation reach real condition? I would maybe for the ANN. For the ANN, I would say that the data set was taken within a range of +50 to -50 to simulate real world parameter uncertainties, which was chosen from literature. So to simulate +50 to -50 is actually the real world mismatch cases. That was able to use to generate the data for it to be trained online. And if you are asking a question concerning calculation of the SDA, I would say that the point of the way the SDA works is digitally. It finds the best solution that cannot be applied directly to the power converter. So once we find this solution, we cannot directly apply it to the power converter. The best thing to do is to find the solution which is closer to it and apply it directly to the power converter. Please, I don't know if this answers the question because the question was very, very generic. I don't know to which area it is asking for.
Okay, sir. Okay, thank you for your answer. And is there any more questions? Okay, there's a chat in the chat box. Okay. Mr. Husnul Amri said that, sorry if I missed this point. I just got from half end of your presentation. My question is, how do you envision this ANN assisted approach translating from simulation to real hardware, especially considering noise and sensor imperfections? Do we need to add some filter consideration for this case?
Okay, so that depends because currently this system is a first order system because there has no filter inside. To add filter makes it a higher order system, and higher order systems are particularly slightly difficult to control, but then it helps a lot because it reduces the THD because of the capacitor there. So in this approach, it will depend, but technically, because higher order systems like filters are hard to, I won't say hard, but more difficult to control, I'm not considering it here. But to deal with the noise and sensor imperfection, it is possible to actually add noise to the model, a certain range of noise to the model, so that when the ANN is working in real time, our generated noise could also add to the robustness of the system. But then, since this work is currently in its first stage, might or might not add filter. But yes, adding filter will make the system more complex. But then, adding filters helps long prediction, SDA, to make the SDA, the THD across each step reduction better than the current ones. So yes, adding filter would work better, but then it also increase the complexity of the system, and it can also increase the computational time. And for the noise issue, you could also add a range of noise to the system so that when the system is working in real time, your range of noise could also be covered.
Okay, thank you for the answer. Is there any more questions from the audience?
Wilson, I don't think we will have more questions because time limitations. So we'll
Okay.
to the next speaker.
Okay, I think it's enough. Thank you, Sir Joseph. Now I will
Thank you.
return the section to Ma'am Nurul.
Thank you, Wilson. And once more, thank you for your insightful and technically rigorous presentation, Joseph. Please give a round of applause for Joseph Akinwumi. Thank you very much. Okay, now we shall now proceed to the next segment of our programs. I kindly remind all participants to direct any questions to Q&A panel or chat box where they be addressed during the discussion sessions. Okay, now we will invite our next speaker, Ms. Ya-Ching Xiao, who will be presenting on the topic of self-reinforcement learning-based energy management for future sustainable aviation. We will invite you to give your full attention as we continue this enriching exchange of knowledge. Good morning, Ms. Xiao. How are you?
Good morning.
Hello, it's been an honor for me. Okay, to meet you here. Before that, please allow me to read a short biography of Ms. Ya-Ching Xiao. Ya-Ching Xiao is a PhD researcher in aerospace engineering at University of Leicester, United Kingdom. As our keynote speaker, she has a strong foundation in mechanical engineering from Cranfield University and industry experience at General Motors in Shanghai. Michelle also brings a unique blend of academic vigor and practical insights. Her current research is self-reinforcement learning-based energy management for future sustainable aviation, explores how artificial intelligence, particularly reinforcement learning, can be safely applied to optimize energy system in aircraft, contributing to the global pursuit of net zero aviation. Her interdisciplinary expertise promises to inspire new directions and sustainable aerospace innovations. We are truly honored to have Ms. Xiao with us today, sharing her insights and expertise directly from United Kingdom. Thank you for joining us virtually and for your continued support for international collaboration. Let us warmly welcome Ms. Ya-Ching Xiao to the stage. Please. I'm sorry, Miss, we can't hear your voice.
Hello, can you hear me right now?
Yes.
Okay, I will share my screen. Okay, can you hear me and see my screen?
Not yet, yeah.
Hello.
I'm afraid it's still loading.
Okay.
Hello, Miss. Are you with us? Yes. So I think we have technical issue with Miss Ya-Ching. Okay. Hello, Miss. So we're waiting for the connection. Okay. Are you okay with your connection? Are you still mute?
Okay, I have unmute myself.
Okay, that's fine. That's fine.
Um, okay, can you see my screen right now? Um,
Okay.
uh, can you tell me? Okay, good. Let's begin.
Miss, we can't hear your voice. I'm sorry, but we can.
Oh, you
see
can't hear
your-
me right now. It's good on. Yeah.
Um, but unfortunately,
Okay,
your
good.
your slides are not correctly. Yeah, because there's two scripts that you shared to us.
Okay.
You show our face here.
It's good right now.
Yes.
Okay, thank you.
Thank you.
It's my great honor to be invited to give a short presentation at this conference. And again, my name is Yajing Xiao, and I'm currently a PhD student in Green Energy and Transportation Research Group at University of Leicester. And today I'm going to present our work on safe reinforcement learning-based energy management for future sustainable aviation. So let's begin with the background. The drive toward decarbonization aviation has sparked a lot of interest in electric propulsion. Both electrification and hydrogen are seen as some of the most promising solutions for degradation aviation. There are two major paths we can see from the slide: the battery-powered aircraft and hydrogen-powered aircraft. Now, the advantage of the battery-powered aircraft are they're clean, quiet, relatively cheap. However, because current battery technology has a low specific energy, it really limits the scale and range of the aircraft, and they also require long charging time. Another hand, hydrogen is also a clean energy resource with a much higher energy density than battery and can be refilled very quickly. But right now, the hydrogen and fuel cell are very expensive, we know. So another key drawback is that the fuel cell has a relative slow dynamic response and can degradation faster during the power fluctuation. So given these trade-offs, a hydrogen approach that have combined the fuel cell and battery are become our research focus. So the potential of the hybrid power system can only be fully realized by a well-designed energy management strategy. We say it EMS. So in generally, EMS can be broadly classified into rule-based, optimization-based, and learning-based approach. First, let's say the role-based strategy. It is straightforward and easy to apply in the real time. However, because it relies heavily on the predefined shared hold, so their adaptability is limited, especially under the dynamic or uncertainty flight conditions. And second is the optimization-based strategy. There mainly includes the global and local optimization. For example, the global optimization methods, such as dynamic programming (DP), can compute a global optimal solution, but they work in a backward manner, which means they require full knowledge of the entire flight profile in advance. And as a result, they can't apply directly in real time. Another is local optimization methods like the ECMS. They can apply online, but they rely heavily on the system modeling and parameter tuning, which makes them very sensitive to the modeling uncertainty. So to overcome these limitations, the learning-based approach offers a promising solution. We can see from there is the deep learning, reinforcement learning, deep reinforcement learning. So when we say deep learning, we commonly think it is AI. It is usually the neural network, which works like the smart brain that can learn from the pattern from the data. On the other hand, reinforcement learning, it is a model-free framework. That means it learns by interacting with environment. And the last, deep reinforcement learning, it combines the strength of the both deep learning and reinforcement learning. So I show a simple figures about how the deep reinforcement learning work in our application. There are 5 key elements: environment, agent, state, action, and reward. On the left side is the environment, which includes everything we care about in the aircraft system, such as the aircraft dynamics, the power system, weather conditions, and so on, everything in environment. And right side is agent, which is built use a deep neural network. And the agent observes the state of the environment and then they think and take the action. So in response to this action, the environment will update the new state and provide a reward as feedbacks. So this framework can offer a more flexible and modern-free and smart strategy to do the multi-objective energy management problem. However, we still face several algorithm-wise challenges which are less here. First is the manager strategy for EMS and task management. The second is adapt and stability for complex flight conditions. And the last one, and the most important one, is safety of explorations and deployment of the RL-based EMS and addressing the inherent risk of its nature. So in our study, we do the modeling at the component level. I model the electric characteristic, weight, efficiency, and degradation behavior of each major subsystence, including the fuel cell, battery, electric motor. And in terms of topology, we can see from this figure, we can see the high tank cell and the fuel to the DC bus lines through a DC converter. And another source is the battery. It also connects to the DC bus line, but it's DC converter. It means it's proposed side of the motor to the DC bus line and drive the mission. Point calculate during the flight. When this motor selects the EMS hybrid aircraft, the EMS has three main goals: minimize the hydrogen fuel consumption, reduce degradation of both fuel cell and battery, and to make sure the battery state of charge return to its initial value at the end of mission. Here is the detailed framework based on the deep reinforcement learning with the longevity consideration. We have published this work in Energy Journal. We are very welcome to refer to this paper for more detailed information. So this slide shows a brief result of our research. The evaluation of the effectiveness of the proposed EMS we have compared with three different approaches. A particular role-based method like physiologic FL, and optimization-based method DP, and conversion or RL-based method like the DQ network DQN. The result shows that 26% reduction in degradation cost compared to the RL-based EMS approach, and the fuel cell degradation is main contribution to cost difference, mainly drive to outpower variation. So this proposed algorithm minimizes the power instable and then integrate the fuel cell agent. Okay, that's all for my presentation today. Thank you very much for listening.
Okay, thank you, Miss, for your great presentation.
Thank you very much.
Yeah, now, as usual, let's continue to question and sessions. But before that, Ibu Ana want to ask.
Thank you, Manolo. Hello, Miss Tia.
Hello.
Hello. Can you
Yes,
hear my
hello.
voice?
Yes, I can hear you very clearly.
Okay. First, I want to confirm that you are research now in the stage of EMS learning-based
Yeah.
strategy with reinforcement learning. Okay. So the next question is from the many algorithm of reinforcement learnings such as A2C, A3C, why you are choosing key learning algorithm? Thank you.
Because it is model-free strategy, it means we don't need a very detailed physical model to build the whole environment, because a lot of things we need to consider in this problem. So what we can do is let the agent to learn all the things into the environment through the interaction between the environment and the agent, and they learn better and make the optimum strategy. So that is progress to make the brain smarter and do the more and more better strategy through this progress.
So
But I have to say right now it's very difficult to do the real time because it's a system level strategy. So when we have much more computation source and more high speed, we can realize it online. But right now it's just can validate through the software, can't apply on hardware.
Okay, so the key learning is more suitable algorithm to implement for your case rather than another algorithm from the reinforcement learning.
Mhm.
Okay, thank you, Miss Tia.
Thank you very much.
This chat box. Okay, just invite only one questions for this session. Please, Will.
Yes. Hi, Miss Yaching.
Yeah, I can hear you very clearly.
I will listen and I will guide you. I will guide on this Q&A session. So there's one question on the chat box. Uh, okay. So okay. So the question is, how the implanted deep learning methods are keep running in their best path without disturb others. We cannot predict the environment. How to make sure this for safety reason?
Okay. In our model, we use a wind disturbance model. That means we can model the fluctuation of the environment in the during the flight. And in this model, we simulate the uncertainty. And right now, just consider this kind of uncertainty, and it performed very well. We consider different kind of strategy in our model, like the physical constraint and the continuous constraint and the intentions constraint. So we make a safety shield for make sure this constraint can work very perfectly. So to make the safety during the fluctuation, such as the state of the charge of the battery, we can't overcharge or over discharge the battery to make sure it is safety during the flight. It is just an example. So our strategy is need to make the SOC of the battery between the 20% to 90%, and the hydrogen tank cancel out. That is our strategy. And you can see from my very welcome to see the paper that we have published for more details. It's very complex to answer in few sentences.
Okay, thank you for the answer. I think that's
Thank you
all
very
for
much.
the Q&A. The time runs out. So I will return the section leader to Nurul and Bu Mariana. Thank you. 谢谢你.
谢谢。
谢谢.
Thank you very
Okay,
much.
let's give round of applause for Joseph and Yajin Xiao for their insightful presentation. We do hope that we can meet, directly, not virtually like this, okay, in the next occasion. Okay, now let's continue to the next speaker. Well, ladies and gentlemen, it is a great pleasure to welcome one of our distinguished speakers who is joining us live online today. Please join me in welcoming Professor Kamel Haddadi, full professor at University of Lille, France, and senior researcher at the Institute of Electronics, Microelectronics, and Nanotechnology, a joint research unit between the University of Lille and the French National Center for Scientific Research. Prof. Haddadi received his Master of Science and PhD degrees in Electrical Engineering from the University of Lille in 2003 and 2007, followed by his habilitations in 2017. He currently leads the RF2S Lab Space Group, radio frequency sensing and services, dedicated to developing microwave and millimeter wave instrumentations and sensor for non-destructive testing application. His research has resulted in over 150 peer-reviewed publications, and he has supervised numerous PhD students and postdoctoral researchers. Prof. Hadadi is also an active IEEE member, serving on international committees such as MTT-8 RF nanotechnology and MTT-24 microwave or wave radar sensing and array systems. He contributed as an associate editor for both IEEE transactions on instrumentation and measurement, and also IET measurement science and technology. Well, now we are truly honored to have Professor Hadadi with us today, sharing his insight and expertise directly from French. Please welcome Professor Kamel Hadadi. Assalamualaikum, Professor.
Assalamu
Can you hear my
alaikum.
voice?
Yeah, good morning, everyone. Can you hear me? Can you hear me?
Waalaikumsalam. How are you today?
Yeah, good. Can you hear me?
Yes, we can hear you clearly. Can you hear our voice?
Yeah.
Also?
Yeah, I can hear you. So
Okay.
okay, then I can begin. Okay, so Assalamu alaikum, everyone. Good morning, everyone. So the title of the presentation is Microwave Techniques and Tools for Non-Destructive Testing. And in this presentation, so I won't go into many technical details, but I would like to share with you the importance to bring together different skills. So I'm coming from a laboratory which is called IMN, Institute of Electronics, Microelectronics and Nanotechnology, which is located in the very north of France. And we have nearly 500 people in this lab, which include 100 international researchers, which are working hard together. And the core of our activity is focused on macro and nanotechnology and their application. So as you said in your introduction, so I'm leading a group which is called RF2S, Radio Frequency Sensing and Services. And we have built a multidisciplinary teams, which include our field of expertise, which is microwaves or electromagnetic waves, artificial intelligence, mechanical design, system integration, and software integration, combined with automation and robotics. Having all of these skills in a single teams give you the opportunity to develop innovative systems for industrial application. My background is about RF communication, 5G to 6G actually. And as you know, there is an increasing demand of high frequency to go at millimeter waves such as 24 to 40 gigs. Specifically, this is associated to low latency, 1 millisecond with 5G, and we know all of that is typically for games and video streaming. So in this field, I'm still continuing to develop some activity, especially the development of new electronic devices at higher frequency, which combine both data transmission and, for example, indoor localization, but I won't go in details again. And as you can see, when you increase the frequency, the size of the electronic device becomes smaller and smaller, and then it becomes very difficult to measure the electrical property of such device. And then we need to have a new strategy to do that. And we do that in the frame of European project, and we're working mainly between university. My university is Lille, but also some NMIs, National Metrology Institute in Europe, such as METAS in Switzerland, and PR in United Kingdom, PTB in Germany, or VS in Netherlands. And then all together, we're developing new measurement system to ensure traceability at higher frequency. And in this frame, we developed some best practice guide, how to perform some measurement at high frequency, but also we provide some innovative measurements, such as, for example, here on the right side, how to measure 1D materials, such as a nanotube, for example, at higher frequency. Second project is related not only to electronic device, but also to materials. Then we have 4 work packages, coaxial measurement, planar measurement of materials, power measurement, and also last one is about material measurements. And what we do in this kind of project, which involve university and EMIs, but also in this project, some measurement equipment manufacturers such as Keysight Technology or Rodesvarts, we have some interlaboratory comparison. So all together, we measure the same devices, for example, and then we have some comparison. And the main idea is to put some error bars on the measurement and then to give traceability to different users. Also, there is a big demand to go at nanoscale because of the growing of nanotechnology. And in this frame, we combine both 2 techniques. The first one is called atomic source macroscopy, which is typically used to have the topography with nanometer resolution with radar system. And then we combine both and we build what we call the scanning macro and macroscopy, which is a nano radar, which can characterize material or sample with nanometer scale resolution. Then in this frame, we develop some new props. So the size at the end of the tip is a few nanometers, typically between 10 and 100 nanometers. And this probe is brought in contact with the sample, and then it can radiate an electromagnetic fields, and we can measure the local interaction. And we develop also with the LNO, which is the French National Metrology Institute, some new measurement equipment to characterize devices such as, for example, MOS capacitance, which have very low dimension, and then we can have a mapping of this capacitance. Last one is about future industrial applications, specifically semiconductor. Semiconductor is related to the very big deal in the next 10 years, I believe. And then there's a very neat demand to characterize such devices with high measurement accuracy. Then we do that typically on devices which are provided by some companies. So this is one is from ST Microelectronics, which is a capacitance. And then again, in this frame, the most important is to assess the measurement variability, but I won't go into technical details. And I would like to show you this slide where typically what we are using is this kind of probe, which has 3 tips, ground, signal ground. As you can see, distance is 100 micrometers. And these probes typically is used to characterize radio frequency components which are used on mobile phones, for example. And we have to ensure the probe tips alignment. We have to avoid the tilted of the probes in order to ensure a good measurement accuracy. So in this frame, usually this probe is moved manually using a mechanical positioning stage. And what we did is that we have automated and developed a nanorobotic stage. So it is very important to combine all of the techniques, mechanical design, nanorobotics, radio frequency measurement, and then to build our own systems, which has the unique capability to perform automated measurements. So then we use some nano positioning stages with, as you can see, resolution is in the order of 1 nanometer. And the probe can be moved in all of the direction, X, Y, Z, but also in rotation. Okay. Then after the mechanical design, of course, we go to fabrication of the probe station. So we automate everything using LabVIEW. We have a camera systems. We have the controller. And this is typically what we can develop in our lab. Then we can move in all of the direction. And I won't go in details, but for example, if you use a conventional system, we have 90% of measurement error when we measure a capacitance on 1 femtofarad at 10 gigahertz, and this error is reduced to around 8% with our systems. Then after that, what we did is that we have also used artificial intelligence tools in order to automate the positioning of the probe on the device under test. We used first any vision assistance from LabVIEW software, and then we have moved to image recognition using YOLO, and we have achieved a very nice and accurate measurement with a high-speed detection, and even in different configurations. For example, with dust, with different measurement scenario, with different lighting conditions. So the system is very robust. And now we have industry which are interested to have this on their solution. So also we are working on microwave characterization of different materials. So the technique was established. Usually we use a system which is called a vector network analyzer, which is connected to different sensor, and then we can characterize some materials using microwaves. The main problem of this technique is that this network analyzer is oversized in terms of size, wide in terms of cost also. But microwaves have a lot of benefits, such as low power, non-ionizing, they have high sensitivity, they can be used in a non-contact manner. So our goal is to develop some microwave techniques with our own solution and to avoid the use of a vector network analyzer. So in this frame, we develop our own network analyzer. Typically, we do that with students, with bachelor students, and the system are very low cost, and they can provide the same capabilities as commercial vector network analyzer. We can do that also at higher frequency, between 55 to 65 gigs, using our clean room. Then the network analyzer is very compact, as we can see here on this slide. And then after fabricating, what we can do is, for example, to connect one antenna to our systems, and then we can have a free space microwave monitoring of water content, for example, in concrete. So it means that we can measure the water content in a concrete in a non-contact manner. We just send a wave, the wave is reflected back, and after modeling, we can retrieve the moisture content. Recently, we also use this technique to measure the conductivity, the RF conductivity of composite materials during the fabrication process with a company which is called Adamant Composite, which is located in Greece. This is very important to do that in order to improve the electrical properties. We use also open-ended coaxial probe. The system is very simple. Sorry, you have a probe which is in contact with the liquid materials or biomaterials. Here we're working on potato tuber, and then we can have the electromagnetic properties of these materials. And yeah, I won't go in. Yeah, maybe I can show very quickly the video, because time is running. So what we did also, we have used nanorobotic stages in order to improve the solution and to have an accurate positioning of the probe in the liquid sample. Sorry. Then doing this, we have demonstrated that we can have a measurement accuracy which is reduced to 0.2% because we have an accurate positioning in comparison with the commercial solution, which typically give you a big error of 5% of the amplitude of the complex permittivity, which is quite high. We are working also with University of California, Irvine in US. We have extended this scanning microwave microscopy and coaxial probing to measure the electromagnetic property of a single living cells. There is a big demand to understand the electrical activity within a living cells. Also, for example, for the cytoplasmic membrane, and also to see how the cell reacts with, for example, when we inject some nanotechnology materials. And finally, we have a last project which is related to 2D materials such as graphene. And my main idea is to use graphene as a shielding materials and to see if when we inject a wave, if the graphene sheet can block the waves. There is some commercial solution, but they are not well suited for our application. And then in this frame, we develop our own systems, as we can see here, which is quite simple, a vector network analyzer. And then we have some plates when we put the graphene in between, and then we can measure the reflection and transmission properties. And finally, so this all of this work has been performed by PhD students, training students, postdoc. They are all here, and I would like to thank them for their work. Thank you very much.
Okay, thank you very much, Professor, for your insights. Very insightful for us. And now, as usual, let's continue to questions and answer sessions. Please, Wilson.
Hi, Sir Kamel.
Hello.
I'm Wilson, and I'm the one guiding this Q&A session. So for the audience, is there any questions according to the materials that being presented by Mr. Kamel? Okay, so there's one question from Mr. Muhammad Ilyas Hadikusuma. Maybe these are some silly questions. First, are there any other implementation of this technology for non-communication field implementation? Second, based on the wafer technology, do you think we should say goodbye to microsystems tech? That's it.
Yeah, sorry, can you repeat the question, please? I'm not sure to understand.
The question is in the chat box. Sorry.
Okay. Thank you very much for these questions. So are there any other applications for non-communication field implementation? Indeed, what we're doing now, we're shifting for other applications than communication because electromagnetic waves, especially microwaves, they have the ability to penetrate materials. So then we can use for non-destructive testing, which is the title of my presentation. And the main idea is to have some information about materials, about the health of materials, but without destroying them. So it means that we can send the materials, for example, on a potato, what I show, and we can measure the sugar content in a potato. And then from this is very important from the industry to know that, because potatoes, they are stored, for example, at very low temperature, and then at low temperature, they produce sugar, and we need to assess that. And so then our goal is indeed to develop systems for non-destructive testing and not communication. And yeah, and for the second question, if I completely understand, do you need to say goodbye to macro systems? I don't think so, because in a conventional system, so we have still power. We need power. So main idea is to combine macro systems and nano systems. Nano system will provide high frequency, high speed data rate, but they have to combine with macro system, which can handle high power.
Okay, thank you, sir, for the answer. Okay, I think it is time to end this keynote session because the time runs out. And thank you, sir, for the presentation. I will return the session back into and Bu Mariana.
Thank you for the organization. Thank you. Bye-bye.
Hello, Assalamualaikum, Prof. Kamel. Hello, Prof. Kamel. Can you
Hello.
hear me?
Yeah.
Yeah, Assalamualaikum, Professor.
So,
Actually, we have waiting for you to meet you in this month, but yeah, I heard about your healthy issue, and we hope you are speedy recovery, and can wait to meet you on January 5, 2026.
thank you for your kind words, inshallah, and thank you very much.
Thank you, Professor.
Thank you.
Okay, please give a round of applause for Professor Kamel Hadadi. Yeah.
Thank you.
Okay, distinguished guests, esteemed speakers, and fellow participants, as we draw this session to a close, Allow me to extend our deepest gratitude for your present and active engagement throughout today's sessions. So we are particularly grateful to our keynote speakers, panelists, and for these thoughtful contributions and to all the attendees for the spirits of inquiry and collegiality that has defined this event. On behalf of the organizing committee, I thank you once again for your participations. We hope that the insights gained today will inspire continued dialogue, research, and innovation in your respective fields. We look forward to welcoming you again at the future conference. And now I hand the program back to Master of Ceremony. Until then, thank you and have a pleasant day.
All right, thank you very much to our speakers and moderator for expertly guiding us through the keynote session. Ladies and gentlemen, we will now proceed to the parallel session 2. Today's parallel session 2 will be led by our distinguished session chair, room in the main room. And the title of session 2 is Informatics, Electrical and Electronics Field. The session chair is Miss Unita and Mr. Suharsono. We would like to remind once again that all participants and presenters that attendance in all scheduled activities is required in order to retrieve the certificate. And the best presenter announcement will be delivered at the end of today's program. Thank you and welcome to the parallel session 2.
Assalamualaikum warahmatullahi wabarakatuh. Welcome, participants, and thank you. And now we were in room 4 for the last parallel session. And we have in this parallel session, 6 papers to be presented, and the first presenter should be Pak Muhammad Ilyas Hadikusuma and Adam, and then the third one is Ahmad Marzuki, the fourth one is Mario Roal, the fifth presenter is Dwi Harjono, and the sixth one is Abdullah Afif Putra Buana. So are everyone already here, the presenters? And for these 6 presentations, each speaker has 10 minutes for the presentation and 5 minutes for questions. And I kindly ask all presenters to keep within the time limit so they can stay on schedule. And for the audience, please mute your microphone, and we will take questions immediately after each talk. And please feel free to post your questions in the chat, and we'll read them out during the Q&A. And to all speakers, please be ready before your presentation and let me know if you have any technical needs. So let's begin. Our first speaker is Muhammad Ilyas Hadikusuma, with the title of the paper is Implementation of IoT-based Microcontroller System for Monitoring Genset Fuel Tank Levels at BTS Facilities. Please join me in welcoming Pak Ilyas Hadikusuma. And yes, please, sir. Time is yours.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Thank you very much for the opportunity for me. Okay, good afternoon, everyone. Can you hear me?
Mohon izin Pak Ilyas, belum terdengar suaranya.
Yes, me. Can you hear me?
Yes.
Okay.
Thank you.
Okay. We are the researcher from the State Politeknik Pontianak. We would proud to present our research entitled Implementation of an IoT-based microcontroller system for monitoring genset fuel tanks levels at BTS facility. This work is being presented at this forum. Okay. This is the brief presentation of what we going through. Yeah, the background until the question 8. We will go one by one. Okay, the background. The base transceiver station, or BTS, are the backbone of cellular communication networks. Many BTS, especially primary power sources. Currently, full level monitoring is done manually, mostly, I believe, which is highly inefficient, time-consuming, and costly. Furthermore, knowing only the full height is insufficient for them. What operators truly need is actual volume in liters. And then, therefore, our objective was to build an IoT system for real-time full volume. This is the proposed solution. We have 3 parts. First is level sensor module. Second, data processing sensor. And the last is monitoring system. Actually, the level sensor use is the improvement from the previous research. Yeah. Because the previous research has a lack linearity. And the data processing sensor, we use not MCU ESP 8266 processing, plus the problem calculation program inside. Okay, in monitoring system, we involve IoT communication like bling and telegram. And also we provide a local LCD display for the operators. Okay, next slide. This is the picture of the proposed solutions. We have a level sensor module. I think I have a mistake for the monitor because it should be divided into hard processing and monitoring system. What you see here is the sensor module. We have 360 read switches. We constructed at 0.05 centimeter spacing for the best resolution. Yeah. Well, not just like that. We have a voice system actually here. The voice system. This is the real module. Yeah. If you see that the specific features there, that's a strong, easy to, you know, what is it? What is it? Mengambang. But we put the neodymium N52 for the best response. Yeah. This is observation feature in the PT Indosat Tbk. Yeah. We have the type of tank, full tank. We have the information about the volume. Okay, so we use this geometry of the tank to calculate the volume. Okay, this is a mathematical model. I borrow it from Banderas, yeah, from Banderas Research, Banderas and France. So he described that the formula for calculating the volume, the tank volume. You can see the, what is it, legenda maybe? Length is L is length of tank, radius tank, and H. Yeah, can read, I believe. This calculation, we put it into the program. Now, this is the flowchart. First, start with the initiation to check the all input-output module. And then will be recheck again. And then doing calculation. And then preparing or make sure is that a real linear data or not. The recording and then sending to the Blink server, yeah, and etc. until finish. This is the implementation result. Yeah, we have the manual here. If you see my mouse, this is the manual at here. And then this is the result of the detection. We send it in blank and telegram. Yeah. This is the blank and also displays the data. Then this is the result. Our results demonstrate that the system is highly accurate. The overall mean error is only 2.03%. As you can see from the table here, the error tends to increase when the full level is very low, ranging from 1.36% to 3.38%. This chart is also show a highly linear relationship between the sensor reading and the actual value, with the R-squared value of 0.9955. That's indicating the high consistency and reliability. As a conclusion, this we have a tree. The system is already successfully implemented there, but actually not really implemented because we have several work to do. Yeah. And then the accurate volume data, we have a 2.03% error, and the data can be accessible via LCD, Blink, Telegram. This is why I don't say it is really successful, because we almost forget the thing that should be, you know, what's it? Tutup apa? Cannot be open, or maybe the rain will be in the tank. So we forget that. Maybe another chance to improve it, the system. Okay, we have a problem too to recalibrating for in the low level accuracy. This is some references we use as a guide for us for building the system. And that's it. This is our team. Thank you very much. Okay, Ben, the time is yours now. Hello, Bu Yunita. I'm still there. I can't hear you. Hello, Bu Yunita. I'm finished.
Oh, wait. Okay.
Thank you, Mr. Ilyas Hadikusuma, for your presentation. We now move on to the question and answer session. There are two participants. You may raise your hand to ask directly or write your question in the chat box. Okay, any question? Miss Yunita?
Where's everybody?
Yes. Hello?
Yes,
Any question to
Pak Sono.
Yes. Any question to participants?
I guess I'm just asking
Yes.
about this. Do you have what kind of potential operational or cost savings that can telecom operators expect from implementing this IoT-based monitoring system?
Well, actually, we can't calculate it very well, but we believe the volume of the tank is so huge, and you know, if we have maybe lost 1 or 2 centimeters, it will cost for the institution. It's very expensive because you know how much spray to the barrel for that. This will be the loss for them if not.
Okay, that makes sense. Yes, okay. And can this system be integrated with predictive analytics or for fuel consumption forecasting in the future? I mean, like, yes.
Yes, of course.
Do you plan to work on that in the future?
Well, if the government give me $100, no $100.
I don't think $100 is enough.
Okay.
Yes. So, is there any other questions from the participants, other participants or audience? I guess if we don't, if there's no more questions, we can continue to our speaker. Thank you again, Pak Ilyas Hadikusuma.
Thank
And
you,
we thank you.
everyone.
That was a really interesting presentation. Sorry. And we now move to our next speaker. Our next presentation is by Adam, with the title of his paper is Geographic Information System for Predicting Electrical Power Potential on Solar Panel Rooftops using Satellite Imagery based on Artificial Intelligence. So, Adam, yes, you may now present your paper. Thank you.
Thank you for the time. Can you hear my voice?
Yes, we can hear you good.
My screen and my voice is different account because now I'm as an operator and as a presenter also.
Okay. Okay. So yeah, okay, you're good. Thank you, sir.
I will share. Right. All right. Can see my slide.
Yes, we can.
Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today I will present our research, which is our research team. The title is the Geographic Information System for Predicting Electric Power Potential on Solar Panel Rooftop through the Satellite Imagery based on Artificial Intelligence. Okay, this is the problem and the potential versus the reality in West Kalimantan. Actually, Kalimantan has a significant solar energy potential with 20 gigawatt due its occasional location, but the current authorization remains very low, only 7.54 megawatt. And this is the electrification gap. The Kalimantan Barat electrification ratio at the end of 2024 has only reached 94.23%. And this is the core problem. Investment of rooftop solar panel is fired by the scarcity of spatial data, accurate information regarding building roof characteristics such as area, shape, orientation is unavailable for optimal power potential calculation. So the objective of the research is we are develop an AI system for detecting and recognizing building rooftop from satellite imagery, and we built a web GIS application to estimating the potential energy from solar panel based on rooftop area and location.
Excuse me, Padam.
Sorry?
Yes, you are still in the title slide.
Oh.
Yes. It's not changing the slides.
Right. I will. Yeah.
Yeah, good. Thank you.
So the methodology, what we do in this research is we build our AI model. We are using YOLO PX segmentation for simultaneous detection and segmentation rooftop area. And we developing the web GIS system. We named it SolarBoost V2 using Laravel Plus and Plus JS. And also the system workflow is when the imaginary input, and then the processing, and the rooftop is recognized by yellow VX, and then the segmented area will be analyzed, calculation the power prediction, and also visualize the result. Okay, the architecture of our research is using WebGIS, Lisbon API, machine learning model, and database. The key feature is the map is used for interface for location selection. The user dashboard is for prediction history, and the detail page is for the display the estimated power potential. And this is our model testing result. We are using the total 530 images. It's divided by 180 training and 450 validation images. And also we have trained with 100 epoch, and the training performance result using a model is most reach the 64.33% for MAP, and the precision is 64.08, and the recall is 90.80%. From this result is the model demonstrate a very good performance without indication of overfitting. But we have roots mean square error is about 26.36%. This is such a big problem of our research. We have a high error. It's identified because of the shadow, complex roof shape, and the blur image quality. So the conclusion is the system is successfully developed using AI and YOLO segmentation, and the accuracy by the external factor such as vegetation of shadow, complex of roof shapes, and satellite image quality. And our limitation is the model still detecting non-roof object like a ground and share similar color or feature. And for the future, we have a recommendation for the development. The first is utilize drone imagery to obtain the higher resolution and reduce the shadow effect. And the second, model integration with drones. And the third, a more detailed cost calculation feature, like adding a feature for more detail, installation cost, and the estimation calculation. Okay. Effect contribution for West Kalimantan. The CSIS provides concrete solution to address the electrification gap by leveraging the enormous solar energy potential. And this technological innovation is integration of AI YOLO V8 segmentation with VIS, creates an innovative platform for special analysis of renewable energy. The SolarBoost V2 application can serve as a model for developing similar system in other regions of Indonesia and contribute to the national energy transition toward clean and sustainable energy. Thank you. That's all. So, moderator.
Okay, thank you, Mr. Zainal, for your presentation. Next session question and answer to all participants and presenters. Okay, please raise your hand to ask directly or write your question in the chat box. Okay. Wait, question. I'm Thank you for Mr. Adam for your presentation. I have a question for you. You mentioned difficulties in detecting objects that share similar texture or colors. How significant is the false positive rate, and what strategies do you plan to implement to mitigate this issue?
Sorry, can you repeat your question, or you can type on the chat box because the sound is
Okay.
bad.
Okay, wait. Okay.
Right.
Yes.
Okay. Yeah. As I mentioned that our system is still detecting non-rooftop object with similar texture and color. So the significance of the false positive is almost what we say in the error is almost 23%. It's bit high error. So our mitigation strategy is for the next research we will create we obtain the training data using drone, yeah, for higher quality of the image, and that's it.
Okay, thank you. Back, Miss Yunita.
Thank you,
Yes.
Pak Adam, for
Yes.
your presentation. If is there any more questions from the audience or participants? So I don't think we have any more questions. So we can now move to our next speaker, which is Pak Ahmad Marzuki with his, and he's going to present his research paper with the title of a noise reduction using Kalman filter in INA 219 current sensor application for precision and accuracy. Pak Ahmad Marzuki,
yes,
time
thank
is
you.
yours. Thank you.
Good afternoon, Ms. Yunita and Mr. Suharsono for moderating this session. I do hope you will hear my voice clearly.
Yes, we hear you good, sir.
Okay. Wait a moment. My paper title is a noise reduction using Kalman filter in INA 219 sensor, and for easiness, we call it INA sensor, application for precision and accuracy. Okay, this is I forget, yeah, I forgot that this title appear because any student come to me, they failed to use INA sensor because its output is very unstable and also not accurate, not precision. Okay, this is why we use the title. This is my design system. The main object of my paper or my research is DC current sensor atau INA sensor. We have to load resistive and inductive load. For inductive load, we use motor. We use DC motor, and we also use LN298 motor driver. Okay. This is a Kalman filter equation. There are one to five equation. 1 and 2, this is prediction, and for 3, 4, and 5, that is update. Okay. Okay, I want to. Okay. This is the flowchart of programming in C language. Okay, this is the output of my experiment using a Kalman filter. For the blue color, for the blue color, this is the output of the sensor, and another color is the output of the Kalman filter. For resistive load, yeah, this is the graph. Okay, we use another result. This is for disturbance, sensor output with disturbance. This is for the blue color is the sensor output, and the orange color is Kalman filter output. Okay, next. This is the variant, output variant of sensor and Kalman filter for resistive load. For resistive load, okay. I want to. Sorry. Okay. This is for resistive load. Actually, the experiment of the Kalman filter is very good because the variant is smaller, much smaller than the variant of the sensor output. So Kalman filter is working nicely. Okay, next. This is how to choose optimal key constant in resistive load. We use in the resistive load, we use the key constant 0.5 because the variant is if the smallest for resistive load. Okay, next. And this is the sensor and the sensor in a sensor and KF output with inductive load. This is for inductive load. This is a D is a duty cycle, 59% for disturbance the input of the motor. This is D equal to 78% for disturbance in input motor, and this is the last is D or duty cycle equal to 59% to disturb the input of the motor. And from this graph, the Kalman filter output is relatively linear, relatively stable. The blue color is the sensor output. So if we didn't use the Kalman filter, so this is the output of the sensor without Kalman filter. But with Kalman filter, the orange line is very stable and not stable and accurate, more accurate. Okay, next. This is another duty cycle. Okay, next. This is another duty cycle also. And then this is the KF output, Kalman filter output with different key. This is, we can use one of the value of the different key. It depends on the characteristic, load characteristic, and the size of the load. Okay. Now this is the sensor atau INA sensor and Kalman filter output with different duty cycle. This is, yeah. In Kalman filter output variant is much more smaller than sensor output. So why Kalman filter is very good to reduce the noise for accuracy and stability. This is the conclusion. The end of my paper. The conclusion results show that the variance value of the Kalman filter output is much smaller than that of the sensor output, both for resistive and inductive loads. The output of the standard Kalman filter, which has been implemented by microcontroller, are influenced by the value assigned to the noise sensor covariance metric R and the process noise covariance Q. Next conclusion, with a value of R equal 100 for resistive load, the value of Q equal 0.5, while for inductive loads, DC motor, the value of key optimal equal to 0.05 can be used optimally. In most applications, the use of the INA sensor cannot be used directly because the output still contains significant noise, both on resistive and inductive load. Thank you very much for giving me presentation. I return to moderator, Ms. Yuna, Ms. Yunita, and Suarsono. Thank you very much. Hello, moderator.
Thank you, Pak Ahmad Marzuki, for your presentation. It was really a good insight. So what I wanted to ask is, is there any questions from the participants or audience? Oh, I think I can see here from Pak Ilyas Hadikusuma in the chat box, and he asked about how to model the system, which in this case is the INA sensor, in math way, so match with Kalman filter. Are there any besides or other than Kalman filter, sir?
What are the limitations using the standard Kalman filter in this context?
From the first one is from the Pak Ilyas.
Yes.
The question, the above.
Yeah, the question of Mr. Ilyas. What are the limitations? Yeah.
No, the other one, the before that.
This is the interesting paper, how to model the system sensor in math way to match with Kalman filter. Are there any way beyond KF? Oh yes, another filter is traditional filter by use electronic system, but the traditional filter is not good for fast response, and then so we use Kalman filter rather than another filter. But Kalman filter is very popular to use in a dynamic system. For example, in control DC motor. Yes, this is maybe, I don't know, maybe another filter we can use, but I know only two filter: traditional filter with electronic circuit and the Kalman filter. Maybe this is my answer. Pak Ilyas. Please comment if my answer is not clear.
This already said, thank you, sir.
The second question, what are the limitations using standard Kalman filter in the context, and under what condition may it fail to track accurate current values? Yeah. The limitation of the Kalman filter is not accurate if the system is not dynamic. It is very very useful if the system is dynamic system. And that is my answer, Pak Ilyas. Oh yes, yes. If Kalman filter used in the moving goods, for example, for measure fuel in the tank of the motorcycle of car, it is very difficult because the moving is unpredictable, very unpredictable, because the condition of the road. That is my answer, Pak Ilyas.
We can join together, sir. 100 million to
Thank-
Vias.
Yeah.
We can join together.
Okay, no problem.
Yes, I think we already Pak Marzuki and Pak Ilyas already have a plan together to work for the next research. Sorry.
Okay, thank you.
Thank you very much, sir. That's really the answer satisfied from the person that asked the questions. Thank you very much.
Thank you very much, moderator.
Thank you again, Pak Ahmad Marzuki, for your presentation. Now we move to our next speaker, Pak Mario Roal, with the title of the paper is Evaluation of Electrical Energy Performance in the Electronics Workshop Laboratory Building of Politeknik Negeri Pontianak. So, Pak Mario, yes, time is yours for your presentation. Thank you very much.
All right. Thank you, Bu Yunita. With your permission, I would like to present in Indonesian for better clarity. Thank you. Okay. Baik. Okay, thank you. Can you listen me? Check sound.
Yes.
Ya. Judul materi yang akan saya paparkan adalah analisis kinerja energi listrik pada bangunan gedung di Laboratorium Bengkel Elektronika Politeknik Negeri Pontianak, di mana tim penelitinya yang ketuanya adalah Pak Medio Notaram, kemudian Pak Wendy Yuniarto, Pak Hasan, dan saya sendiri. Baik, saya akan paparkan di mana latar belakang penelitian mengacu kepada peraturan ESDM nomor 14/2012 tentang penggunaan energi kurang dari 6.000 setara ton minyak per tahun. Wajib melaksanakan manajemen energi dan penghematan energi. Ya. Kemudian untuk di peraturan pemerintah nomor 70/2009 konservasi energi untuk perseorangan, badan usaha dan lembaga pemerintah yang memanfaatkan energi. Selanjutnya PP nomor 33 mengenai sektor bangun gedung dengan penggunaan kurang dari 500 setara ton minyak per tahun atau 5.826. Ya. Kemudian surat edaran Kemendikti nomor 4/2025 tentang instruksi kebijakan efisiensi energi termasuk penghematan belanja daya dan jasa terkait penggunaan listrik. Selain itu juga diambil penelitian ini berdasarkan berulangnya kerusakan pada utility ya, peralatan air conditioning dan lampu penerangan pada periode yang berdekatan, jadi lebih sering rusak gitu, menjadi perhatian khusus dalam penelitian ini. Oke, di mana masalahnya adalah kinerja energi yang buruk pada bangunan gedung, di mana kasus ini kami ambil dari laboratorium dan bengkel elektronika yang berdampak pada konsumsi energi yang tinggi dan cenderung tidak efisien. Hal ini mendorong percepatan kerusakan atau memperpendek usia pakai pada peralatan. Mana tujuan penelitian ini adalah melakukan tinjauan serta analisis kinerja energi listrik secara mendalam, serta mengidentifikasi dan mengkuantifikasi potensi konservasi energi di bangunan gedung, laboratorium, dan bengkel elektronika pada kampus Politeknik Negeri Pontianak. Untuk urgensinya, kinerja energi dan konservasi energi menjadi isu penting di era modern, sehingga efisiensi energi dapat dilaksanakan tanpa mengurangi kenyamanan dan produktivitas pengguna, termasuk dalam operasional peralatan, instrumen pengukuran, AC, lampu penerangan, pompa air, dan peralatan listrik lainnya. Untuk kinerja energi listrik dan kualitas daya, di mana titik pengukuran ini menurut SPLN berada di titik terdekat di mana instalasi milik pelanggan disambungkan kepada terminal dan meter transaksi milik PLN. Di mana penelitian ini durasi pengukurannya paling sedikit 7 hari kemarin pada kondisi instalasi beban listrik beroperasi dengan beban dan siklus normal. Untuk kualitas daya mengacu kepada kesesuaian karakteristik suplai listrik, tegangan, frekuensi, dan gelombang dengan standar yang ditetapkan. Parameter dalam pengukuran atau penelitian ini yang diambil adalah harmonisa, di mana polisi listrik berupa gelombang frekuensi tinggi yang menumpang pada gelombang listrik fundamental, yaitu frekuensi 50 Hz, diukur melalui total harmonic distortion atau THD untuk tegangan dan arus. Kemudian ketidakseimbangan tegangan antar fasa, di mana kondisi di mana magnitudo tegangan pada ketiga fasa RST tidak sama besar dan atau pergeseran fasa tidak tepat 120 derajat disebabkan oleh ketidakseimbangan pemasangan beban. Kemudian ketidakseimbangan arus, di mana kondisi di mana arus yang mengalir pada ketiga fasa tidak sama besarnya. Otomatis karena tegangannya tidak seimbang, ya otomatis ketidakseimbangan arusnya pasti juga sama. Parameter faktor daya kami mengacu ke standar sumber PLN itu harus lebih besar dari 0,85, tegangan lebih kecil dari 198 atau lebih besar dari 231, itu udah perlu kita evaluasi. Terus ketidakseimbangan tegangan lebih kecil dari 3% menurut ANSI ini C84, ketidakseimbangan arus lebih kecil sama dengan 20%, THD tadi ada lebih kecil dari 5%, mengacu ke permen ESDM, THD arusnya lebih kecil atau sama dengan 5%, mengacu pada permen ESDM, dan frekuensi 49,5 sampai 50,5 Hz berdasarkan permen ESDM juga. Oke. Dari data yang diambil, beban terpasang pada gedung laboratorium elektronika, itu terlihat bebannya yang dipasang adalah jenis lampu TL 40 watt, lampu LED 10 watt, AC 2 PK, AC 5 PK, komputer. Di mana terlihat pada fasa T di sini, total daya dari beban yang terpasang itu jauh lebih besar dibanding fasa R dan S-nya. Untuk gedung bengkel elektronika sendiri, lampu TL 40 watt itu terpasang 1360, 960, 480, kurang lebih di fasa R-nya agak besar. Terus lampu LED AC 2 PK komputer totalnya di fasa R 5400, fasa S-nya 8960, dan fasa T 8760. Ini masih kita anggap masih aman gitu, walaupun hampir di fasa R-nya itu terlalu kecil ya. Data beban terpasang menunjukkan distribusi daya yang tidak merata antar fasa, terutama pada gedung laboratorium elektronika, dengan perbedaan signifikan antara fasa R-nya sebesar 5000 watt dan fasa T-nya 21.150 watt. Dari hasil pengukuran kinerja energi, untuk faktor daya karena kita mengacu ke standar PLN harus lebih besar dari 0,85 untuk di gedung yang kami analisis ini datanya masih memenuhi syarat lah untuk aturan standar PLN itu. Kemudian untuk tagihan rata-ratanya sesuai standar masih, untuk frekuensinya masih aman. Cuman di sini yang agak perlu diperhatikan adalah total harmonisa arus THDI tercatat 8,879%, melebihi standar yang ditetapkan, yaitu lebih kecil atau sama dengan 5%. Hal ini memerlukan tindakan perbaikan melalui pemerataan beban antar pasah. Kesimpulan dan rekomendasi di mana dari hasil evaluasi dan analisis yang dilakukan, jadi kami ambil kesimpulan bahwa kinerja energi listrik berada pada kondisi optimal dengan faktor daya sesuai standar, yaitu di atas 0,9, tegangan dan frekuensi dalam batas normal, ketidakseimbangan tegangan memenuhi kriteria 1,81%, ketidakseimbangan arus cukup besar 12,3%, mendekati standar, menunjukkan pembebanan fase tidak merata. Agak besar di sini. Jadi yang perlu diperhatikan adalah ketidakseimbangan arus. THDI melebihi standar 8,879% akibat ketidakseimbangan beban terpasang. Jadi saran yang dibuat dari hasil evaluasi dan analisis data ini yaitu dokumentasi instalasi. Jadi perlu adanya gambar instalasi lengkap pada gedung laboratorium dan bengkel untuk evaluasi dan action dari analisis yang dilakukan ini. Kemudian adalah survei berkala, dan kalau memang ini sudah dilakukan semua, yaitu akhirnya adalah pemerataan beban. Jadi demikian paparan yang dapat saya sampaikan. Terima kasih, saya kembalikan ke moderator.
Okay, thank you for your presentation, Mr. Mario.
Okay, thank you.
We now move on to the question and answer session. There are two participants. You may ask directly or write your question in the chat box. Okay, we have a first question addressed to Mr. Mario from Ms. Nanda Rusda Saufa. Here is the question. What measurement instrument and procedure did you use to collect the power quality data for the laboratory or workshop building?
Instrumen. Oke, thank you. Untuk instrumen yang digunakan berupa alat-alat ukur, termasuk power quality, untuk mendata dan melihat kualitas tegangan, arus, dan harmonisanya. Gitu. Jadi dari data itu kita kompilasi dan kita analisis sesuai dengan standar atau permen standar nasional yang berlaku. Itu aja. Terima kasih, Pak Suarsono.
Thank you for your answer, and Ms. Nanda for your question. Okay, Ms. Yunita, next presenter, please.
Thank you again for the excellent presentation, Pak Mario. And now we will now move to our next speaker, Pak Dwi Harjono, and he will present his paper with the title of Modular Power Station Prototype, a Responsive Solution to Dynamic Energy Demands. So, Pak Dwi Harjono, the time is yours to present your paper research.
No access, Pak Dwi.
Can anyone see if the Pak Dwi Harjono is available and the participant? No, okay. So Do you know there's someone to substitute or Pak Dwi to present his paper? Let's wait for 1 minute, 2 minutes maybe. Maybe Pak Dwi it's a bit late or something, or just lost the link to Zoom.
Maybe Pak Dwi is sleeping.
Enak nih Pak ya, mendung. It's cloudy, so I think it's good to have a nap. Yeah.
Coffee break, Miss Elias. Coffee break.
Okay, so I think let's just continue to our next speaker. And we will have Pak Dwi present if he's ready after the last speaker, after the next speaker. So the next one should be Pak Abdullah Afif Putra Buana with the title of the research paper is Development of a PLC-based teaching model for induction motor control using an inverter in electrical workshop of Polnep. So is Abdullah Afif Putra Buana available for the presentation? Okay. We lost 2 presenters.
Pak Afif. No.
Pak Afif ada? Pak Dwi ada?
Close the session. No presenter again.
They are all sleeping.
Let's wait until 3:20 p.m. Maybe, as I said, maybe they lost the link or someone can contact them or something.
Yeah.
I think Pak Dwi Harjono and Abdullah Afif Putra changed by Sabanita. Miss Sabanita, please. Please, Bu
I just
Sabanita.
heard, Mister. Yeah, I just heard. Yeah.
Okay, no problem.
Next. Yeah, a good presentation, Mister.
Oh, thank you, thank you.
Your
This is what
presentation very interesting.
this is the one in this session. There is a Madam Miss Sabanita say like that. This is the first person say that my presentation is good.
I think Mr. Hassan should replace them because he's the head of Jerusalem.
Marzuki, your presentation is also it's really interesting. It's really good because you can predict also the.
With Mr. Hassan. Okay, okay.
Can you close this session? Nothing presenter.
Okay. Okay, so I guess we can conclude for this session. So as the speaker is not present, yes, and well, I would like to thank you to all our speakers for their excellent contributions.
We should
and
have
thank you.
our photograph, right?
Oh yeah, yes, of course. Thank you to the audience for your participations and thoughtful questions. And this concludes for our room 4 parallel session. And yes, thank you everyone. And I think we can. I will return this to the main moderator. Thank you very much and have a nice, good rest of the evening. Thank you. Bye. Assalamualaikum warahmatullahi wabarakatuh.
Wow.
Coba Rit, lagi, Nun. Gitu tuh kah?
All right. Thank you very much to our speakers and moderator for expertly guiding us through the parallelization. Ladies and gentlemen, we will now take a 5-minute break for this transition to the best presenter session. And we will come back at 15:20. Thank you for your attention.
Yuk, lagi kita kawan.
Ladies and gentlemen, before we move to the closing session, we are pleased to announce today best presenter. After reviewing all presentation, our session chair have selected 4 presenters who performs stood out. The best speaker goes to Room 1. Congratulations to Mr. Hasnul Amri. Room 2. Congratulations to Miss Aulia Gustiani. Room 3. Congratulations to Mr. Muhammad Maulidin. And the last is the main room. Congratulations to Mr. Ahmad Marzuki. Congratulations to our best speaker. Thank you for your excellent presentation and your contributions to today's event. To all presenters, we truly appreciate your effort and participation. That's bring us to the end of today's INFERT 2025. It has been a great pleasure to host this event. We wish you all a continued growth, innovation, and collaboration as we move forward together in supporting the development of our international academic and organizational excellence. To all speakers, session chair, and participants, thank you for your attention. Enjoy the rest of your day. Keep collaborating and remember, together we grow stronger. Wassalamualaikum warahmatullahi wabarakatuh.
Sudah, silakan. Terima kasih juga yang telah hadir di room Zoom hari ini. Ya, peserta maksimal hampir 500 partisipan. That's very, very amazing. Thank you. Oke, mewakili teman-teman panitia, mohon maaf apabila salah kata, dan sampai jumpa di INFERT tahun berikutnya di tahun 2026. Jangan lupa submit papernya di tahun 2030. INFERT dengan indeks IEEE 2030. Nggak sanggup. Ini Januari itu dari Desember lagi.